Okay. Hi everyone. My name is Neil. The formatting of the slides seems to be a little bit messed up, so I apologize for that. I am a quantum scientist at Riverlane. So Riverlane is a company that's founded by Steve Riley, who was a postdoc here actually at University of Cambridge, and we look at bringing the world of quantum computing into the real world, essentially, the practical applications and implementations of quantum computing. And a massive part of quantum computing is quantum error correction, and I'm going to talk about some of the mathematics behind that. Okay, that's great. So the motivation, this is a motivational slide, and the motivation, I guess, in some sense, the left-hand side is money. But the two barriers, the two regions here, there's a NISQ barrier and there's this quantum error correction region up here. So what's the NISQ barrier all about? So that NISQ stands for near-term intermediate scale quantum computing. So I remembered it, that's great. So what that essentially is trying to use the early quantum computers that are getting built today to get some sort of commercial advantage. Now, the reason that we say that there's this NISQ barrier essentially is to do with the fragility of the qubit. So the qubit is the fundamental building block of a quantum computer, and it's the fragility of the qubits that puts a barrier to the value that you can get out of these near-term devices. And essentially, the reason behind that is you have an algorithm that you're wanting to run, which you can write down as a circuit, say, and there's a limit to how deep the circuit can go, okay? And the limit is because of the fragility of these qubits. So the qubits are very sensitive to noise, and essentially, the deeper your circuit will go, the noise will overcome any computation that you're trying to do, and all you have is just noise. You won't get any signal out of it. So in order to reach these high value applications that everyone believes are possible, you need to handle this noise. And the theory that handles this noise is quantum error correction. And I'm going to talk about some of the mathematics behind that. Okay, so as I said, any quantum system you need to protect from its environment. Otherwise, it's just going to interact with the environment. It's just going to become classical, and if it's classical, you can't take advantage of the quantum mechanics to get the various speedups that are possible. Okay, so what quantum error correction is all about is about building this wall around your device in some sense, so that you can protect your qubits in some way and get your computational advantage. So. Diagrammatically, what we're going to have is a large Hilbert space of, say, a large number of qubits, could be millions, so an n-qubit Hilbert space. And what we're trying to do is carve out some subspace of this, which will represent k logical qubits, and that's where we're going to do our computation. All right. Cool. So the types of it's unfortunate the top of the slide is missing. The types of errors that you can see. So what's the types of noise that come up that you're going to encounter when you're doing quantum computation, right? So I wasn't sure if people knew what a qubit actually was, but at the very top, is this a pointer that was? Ah, cool, right at the top here. So at the very top here, that behind the Zoom thing is what a qubit is, and in its mathematical simplicity is just a two-dimensional vector over the complex numbers. That's all it is, but it's a unit norm two-dimensional vector. So you can just think of a qubit as that, okay? And so we've got a particular basis here, which we've got, so it's two dimensions, so we've got two basis vectors. Our orthogonal basis we call ket 0 and ket 1, okay? This is the notation that quantum scientists use and physicists use as well. Okay, so this is our basis ket 0 and ket 1. And the types of errors that can occur, well, we see what they do to the basis element. So we have the bit flip, which is which is the quantum analog of the classical bit flip. So we've got bits and classical bits, and it's a flip, and the classical bit sends 0 to 1. It's the exact same thing that happens for the quantum bit flip. It just says ket 0 to ket 1 and ket 1 to ket 0. Okay, so that's analogous to the classical situation, but we have the phase flip here. This is something that you don't have in the classical realm. Okay, so what that's doing is it's leaving the ket 0 alone, but it's changing the phase of the ket 1. It's negating the phase of the ket 1. And so these are what you call discrete operations in some sense, but we also have these continuous errors that can be done as well. And really you can do a continuous rotation in any basis, but this rotation that I've described here is in the Z basis. So what it's doing is it's leaving the ket 0 alone, and it's rotating the ket 1 round by an angle of theta. So that's what's going on. So we definitely, so these errors here, we don't have classical analogs at all, right? A general error, so this is a slightly different notation to represent a qubit. This is just a density matrix. A general error on a single qubit sends it to some linear combination where these AKs are operators that are acting on your qubit, and they have a certain property that the sum of these AKs, AK daggers, is 1. Essentially, that's saying that they form essentially a probability distribution. That's what's going on. So an example of this is the dephasing error. So what happens here, essentially, this when you write out the matrix for this, this is essentially a projection onto the ket 0. That's what's going on here. So what that's saying is with your qubit here, you're projecting onto the ket 0 and you're losing any phase. That's why it's called the dephasing error. So this is an example of a general error. And so these are the types of errors that we're going to want to correct for. So what is tricky about, there's a couple of things that could be tricky about this. So for starters, how do you account for, there's an infinite number of errors in this rotation, right? How do you account for correcting for an infinite number of errors? That seems a bit tricky. Also, one of the postulates of quantum mechanics is that if you look at a quantum system, so you're essentially effecting a measurement on a quantum system, the information is going to collapse, right? It's going to collapse into some sort of state. And so how do we do, so essentially what we've got to try and do is correct for these errors, but by not letting the data, the information that we care about disappear. So we need to sort of correct for them without looking at the data that we're interested in. So there are some of the hurdles that we need to get over, right? Okay. So we have this is an example of the classical repetition code up above. So all that happens in the classical repetition code is you repeat the bits that you're interested in. So we're going to send one bit, we send one bit, we send three versions of that bit. So 0 gets sent as 0, 0, 0, 1 gets sent as 1, 1, 1. There's a quantum version of that as well, and all we do is that we encode the we're going to encode the basis states ket 0 and ket 1 into our high dimensional vector space. So we've got one qubit over here, but we're going to encode it in a three qubit system. All right. Okay, so what happens if a single error affects this encoded qubit over here? Well, say we have an X error, a bit flip on the second qubit. Okay, so what that's going to do is going to put this bit here and this bit here, and we get this result down here. So the interesting thing about this is that the single error affects the terms in this superposition in a similar way, right? In the sense that the second qubit in this term is different from the first and third one, and it's the same here as well. So we kind of there's some information embedded in the superposition, the basis states, that hopefully we can get access to without having to destroy the actual information, the data that we're interested in, the alpha and the beta. Okay. So the idea is, so what we want to do is we want to try and diagnose this error without looking at the data. And the idea is that you measure the error and not the data. So what we have here is we have our encoded state on it. So we've encoded into 3 qubits, right? Each Y here represents a qubit. So we've encoded into 3 qubits, and we're going to use some ancilla qubits here to try and diagnose the data, right? So these circuit diagrams might be a little bit unfamiliar to you, but essentially, if you have, you can play a little game. If an X error was to happen here, what happens is that when you see one of these dots, it comes down, it follows down the dot. Whenever you see the plus, it goes along the wire where the plus is. So the X error will continue along up here, but then it will kind of be copied down here. So that's what this is, a C0 gate. Yeah. Okay, so if we had a single error on the first qubit here, what would happen is it would get copied down to this ancilla qubit here, and it's an X error, right? So we'd flip that 0 to a 1. Okay, so now you have an X error up here, it gets mapped down to here, flips this 0 to 1, and then you make a measurement here at the end. And that measurement here at the end is going to tell you whether or not you've got a 0 or 1 on this qubit here, right? So a single X error here, by enacting this circuit, it will be mapped down to the first qubit, it won't be mapped down to the second qubit. So what we'll see when we measure out is a 1 and a 0. So a single error on the 0th qubit will have a syndrome. The syndrome is the measurement that's come out here of a syndrome of 1, 0. And you can play the same game for an X error on the second qubit. It will get mapped down to the first and second ancilla qubit, and you have a syndrome 1, 1. So by measuring these syndromes here, we see that they're representing a single X error, right? And the identity will do nothing, so that's nice. But interestingly, if you had a single Z error, so this is, you need to kind of understand how these gates work. A Z error, unfortunately, does not go down one of these C0 gates, right? So a Z error will just trundle along on the data, and you won't be able to detect it. So this particular code is really interesting. It can detect single X errors, but it can't detect Z errors, right? So that's great. We can detect one type of error, but we need to be able to detect all those other types of errors that I mentioned before, right? So at least in principle, we might be able to solve this problem. Okay, so the previous one corrected a bit flip, and we need to try and correct a phase flip, so the Z error. And the sort of solution to that is essentially apply a Hadamard matrix. So the relationship between X's and Z's is given there. Oh, I've lost my pointer, I think. The conjugate of X under Hadamard is just Z, okay? And so you can do the exact same procedure, but just by conjugating everything essentially by Hadamard. So previously, when we encoded a single ket into ket 0 into 3 ket zeros, okay? This time we encode a single ket 0 into 3 ket pluses, where plus is the Hadamard transform of the ket 0, okay? So if you just go through it, all I've just done is basically change a basis. That is it. That's all that's happened. Change my basis, and I can go through the whole procedure again. And that similar code, it will detect, be able to correct Z errors, but it won't be able to detect X errors, right? So given a certain basis, I can detect and correct a single X or a single Z error. Okay, but we want to be able to correct both, right? At least, right, sorry. Okay, so how can we correct both? So a way to correct both is to use what's known as concatenation. So concatenation in the classical world just means sticking two bit strings together. It's slightly different in the quantum world. It's kind of like a double encoding of what's going on. So what we do is we start off by doing our first initial encoding, right? So our initial encoding was to detect the bit flips, okay? So we do the usual 0 to 3 kets, 3 0 kets. And then we just call this a 0 logical, okay? So this is, so we put this L down to represent those 3 ket zeros, right? And then what we do is we encode that ket 0 logical in the other code, right? And so we represent this ket 0 logical as 3 ket plus logicals. so at the logical level, right? And so when you write it out, what you end up having is, so we've done, first encoding was 3 qubits, and each one of those 3 qubits is encoded again by 3 more qubits, 3 logical qubits. We end up with 9 qubits in total. Okay, and this is Shor's 9-qubit code, and this is one of the first error correction codes, quantum error correction codes that was ever discovered. So Peter Shor, hopefully you've heard of Shor's algorithm. It is the algorithm that kind of kicks off the whole quantum industry in some sense. He invented the algorithm to show that you could factor numbers in polynomial time. Okay, and he also kicked off the error correction area as well. So this code is great because it can detect any single X or Z error, and it can also detect a single Y error. So the Y error is the other Pauli matrix that we care about in quantum computing, and it's I times X times Z. Okay, so I'll explain later in a circuit how this actually works in a bit more detail, right? So I've just showed you how to correct for a discrete set of errors, X, Y, and Z. But remember, I talked about rotations, right? That's an infinite number of errors. How are we going to use the ability to correct a discrete set of errors to correct against a continuous set of errors? Well, let's have a look at this arbitrary rotation. Well, it turns out that you can write out an arbitrary rotation in the Z axis as a linear combination of something times the identity times something times Z, okay? And the something's related to, and it's this relation here, so it's cosine theta over 2 times identity minus I times theta over 2 times Z. Okay, so what we're gonna do, and this is where the linearity of quantum mechanics comes to your aid. What we're gonna do is we're going to have our state encoded. So we're going to apply this error to our state. This state here, psi, is encoded somehow. Okay, right? And then I'm going to introduce some ancilla qubits again. So I've not drawn a circuit, but you can imagine that's what's going to happen. We're going to have some ancilla qubits again, and we're going to do that same procedure of these gates that's entangling the logical information that I'm interested with and the ancilla qubits. And when we measure those ancilla qubits, what's going to happen is we're either going to see a syndrome that corresponds to the identity, and in that case, nothing will have happened to our state psi, or we'll see a syndrome that corresponds to the Z error happening. And we see the identity syndrome with probability cos squared theta. It's cos squared theta on 2. Okay. So when we measure the ancilla qubits, what happens? There's some probability that we see the identity syndrome. And if we see the identity syndrome, no errors actually happen to our data the data has collapsed to this state here. Okay. If we measure the syndrome and we see the Z syndrome in the ancilla qubits, the data collapse to the state with the Z error applied to it as well. Okay. So by discretizing our continuous rotation here, we can correct it by just handling a discrete number of errors. Okay, cool. Okay, so essentially we have this theorem then, which is kind of done by that example previously. It's sort of inspired by that previous example. If you have a quantum error correcting code that can correct for errors A and B, it can also correct for any linear combination of errors of A and B. And then the fact that any 2x2 matrix, the identity X, Y, and Z is a basis for any two-dimensional 2x2 matrix, it means that you can correct for any single qubit error if you can correct for X, Y, and Z. Okay, so this is how we are able to correct for an arbitrary number of errors by just using the discrete number of corrections. Okay, so that's cool. Okay, so maybe something, so this was kind of trying to give you an example of what's going on here. Let's maybe see the theory that, I'm going to mention the theory that's underpinning a lot of this quantum error correction. And the theory is called the stabilizer formalism. It was introduced by Daniel Gottesman around 2005, 2006 in his PhD thesis. So what we start off with is the Pauli group. And that's the group that's generated by the complex number I and X and Z. Okay. And when we're thinking about encoding something into n qubits, we look at the n-tensor fold product of this Pauli group. Okay. And what we're interested in are particular subgroups. So again, sorry for the formatting here. Some seems to be lost in translation a bit. So we have a stabilizer group. It's a really simple definition. It's just a subgroup of this Pauli group and this n-qubit Pauli group that does not contain minus identity. It's a really lovely, simple definition. Okay. And essentially what we have is for any subgroup, any stabilizer subgroup, we're going to have something that's a quantum error correcting code. It's called a stabilizer code. And this lemma gives you some properties about the stabilizer subgroup. So start off, it's an abelian subgroup. In fact, it's an elementary abelian subgroup. And the Hilbert space decomposes as a direct sum of some subspaces, which are each 2 to the k dimensional. And each subspace essentially corresponds to a syndrome that you would see when you measured some ancillary qubits. And so there is a particular subspace. I mean, you essentially choose, it's arbitrary which one you choose to be your code subspace, but there'll be an identity syndrome that you're interested in. You make that choice, and that is the code that you are interested in. That's the subspace that you're trying to protect. Okay? And because it's a 2 to the k dimensional subspace, essentially this subspace is representing k logical qubits. So this is how you embed k logical qubits into a n-qubit Hilbert space. And what happens when you are, so if I'm doing some sort of computation and some errors occur on the data, and I make that measurement that by entangled with some ancillary qubits, and I see a syndrome, my state or the space essentially is going to collapse onto the corresponding code subspace with that corresponding syndrome. So imagine my syndrome was like 1000, and I measured that. So when I measured that, I now know that my state is sitting inside the code subspace with that corresponding syndrome. And if I want to get back to my original code subspace, I need to make some sort of correction. Okay. So in our example that we saw, the 9 qubit Shor's 9 qubit code. So these are its stabilizers here. So we have we've got 6 Z stabilizers, which are these pairwise Z operators, and then we've got these weight 6 X operators as well that are the stabilizers. So what essentially is going on is for each three bits, you can imagine, so we've got 9 qubits in total, and we've got, so we break them up into 3 sets of 3, and you see in the first 3, what the Z1 and Z2 and Z1, Z3, what they're doing is checking for X errors on the first 3 qubits, okay? And it's the same for Z4, Z5, and Z4, Z6. They're checking for X errors on the second 3 qubits. And they're doing this by doing a parity check between, say, the first and the second and the first and the third, or the first and the third qubits. And then what happens with these blocks is, so the X1, X2, X3, X4, X5, X6, what that's doing is doing a phase parity check between, the first block and the second block. And the last X operator is doing a phase check between the first block and the third block as well. Okay, so this is how this code can correct for any single error. Right. Okay. So I've introduced quantum error correcting code, but who knows if those codes that I've just introduced to you are actually of any good to us, any use to us, right? So the desired properties of codes and stabilizer groups are, these are some of the desired properties. Right? So obviously you want your code to be able to correct lots of errors, right? That's kind of self-evident, right? You also want the code to encode as many logical qubits as possible. So essentially you've got k logical qubits and you've got n physical qubits. You want this ratio k over n, which is often called the rate. You want that to be as close to 1 as possible, right? Essentially, because if I can only encode 1 logical qubit and I need lots of qubits, I've got a massive overhead, right? And I don't want that overhead to be huge. So if you understand that, essentially, if you've seen some of these dilution fridges for qubits, let's just say that there's, I mean, it's not quite true, but let's just say there's like 10 qubits in 1 dilution fridge, and you needed, I don't know, 1 million qubits. You're going to have a lot of dilution fridges, right? So that's a lot of energy. So you kind of want to minimize that overhead as much as you can. The weights of the stabilizers are low. So I'll just go back to this previous diagram. So the weight is the number of terms, non-identity terms in the operator, right? So Z1, Z2 has weight 2. All those X operators have got weight 6. Okay. So why do you want the weights of the operators to be low? It's essentially because you're going to have to do some kind of circuit like this to extract the information about the error, right? And this the complexity of this circuit is basically dependent on the weight of those operators. So and this circuit involves qubits and also gates as well, gates that are acting on qubits. And those qubits and those gates can also fail. So the way I've talked about it is if these gates are perfect and the qubits that the ancillary qubits are somehow perfect, but that's not true, right? So the more gates and the more qubits that you need to extract the syndrome, the more problems that you're going to give yourself down the track. Right? So essentially what I'm saying is the less likely you can trust the information that's in your syndrome. Your syndrome is not going to be perfect, and the more gates and qubits that are needed to extract the syndrome, the less perfect it's going to be. So this is why you need the weights of the stabilizers to be low. And then also, can it be laid out in a simple architecture? So if you go to any computing like Google or Microsoft or Rigetti or whoever it is, and you look at their actual qubit architecture, the qubits are often laid out on a plane, right? And qubits can only interact with neighboring qubits, right? So again, coming back to this diagram here, I was letting any qubit interact with any qubit, and I wasn't saying how they were laid out. But in reality, there are constraints with the physical makeup of the qubits that say you need to be able to do your computation in a way that fits well in the architecture. Okay, so this here is probably the most famous quantum error correcting code. It was discovered by Cantab in, I think, 97, and it's called the torus code. So what we have here is the torus, and we've just tiled the torus with a whole bunch of qubits, but it's just a square lattice that's been put on the torus. Okay, and there's a code that can be defined on this torus. Essentially, my stabilizers are defined by the squares, okay, and the crosses of this lattice. So I'm going to have Z stabilizers on the squares, and I'm going to have X stabilizers at the corners, so of this lattice as well. Okay, so this code is very interesting for a number of reasons. One, it can correct a lot of errors, not as many errors as is theoretically possible, but it does pretty well. It's a square root. If you've got n qubits, it's a square root of the number of errors that can correct essentially a square root of n. It's terrible in the logical qubit count. It only encodes 2 logical qubits. And the 2 logical qubits come from the topology of the torus. Essentially, it's the homology group that tells you that it has 2 logical qubits, right? So there's this lovely connection between interesting quantum error correcting codes and topology. The weights of the stabilizers are super low. That's one of its main advantages, and it can be laid out on a simple architecture, right? So this can't be laid out in simple architecture because it's a donut, right? But there's a version of it where we can cut the donut and actually lay that out on the table, right? So if you were to ask Google to make a donut of qubits, they'd probably tell you to go away, right? Right. Okay, I think I only have 5 more minutes. So I do have some more slides, but I think I'll just skip them. I'll talk about this slide actually just to this is like a teaser slide in terms of essentially what I'm saying here is the codes that we have today are not really good enough to really get to those high value applications. Essentially, the rates of the codes, so the number of logical qubits they encode are too small. So there's some constraints on the distance. Distance is a measure of how many errors it can correct, and also the number of logical qubits, right? So there's some constraints that we have. So essentially, we have to find, we need to find some good, better codes with better rates and better distance. And the really interesting codes that people are finding just now are coming from highly mathematical objects. So there's some beautiful structures coming from buildings. If you know what buildings are, Brouwer-Tietz buildings. This is the algebraic number theoretic thing. And there's also fiber bundles and things like this. And topology plays a massive role in these constructions as well. So we need to find better codes. They haven't been found yet. In the classical realm, it took over 60 years for people to find the best codes, which are LDPC codes. We're hoping it's not going to take 60 years in the quantum world as well. And I would just, so this was just some fun thing that I was going to show you. We just highlight the real value. Again, I'll leave this slide again. Why we care about this is essentially because it's the driver to unlock these high value applications. Cool, I'll stop there.
Other questions for me?
Yes.
Like, can you can you just like drop some numbers? So order of magnitudes, like what's the state of the art logical to physical qubit ratio? Like what do you need for things like Shor's algorithm?
So I'll give you an example of a costing that Google did for Shor's algorithm. So they costed factoring a 2048-bit number, and they managed to the time for the algorithm was only 8 hours. So that's amazing. NSA, GCHQ would love that, right? But they needed 20 million qubits to do that. And so then if you ask a physicist, well, okay, Google, how many qubits has Google got? They've got 50, right? And controlling 50 qubits and engineering 50 qubits is incredibly hard. So you can imagine how difficult 20 million qubits would be. So that number needs to come down. So the engineering we kind of need to bridge this gap this way. I think the engineer needs to, mathematics needs to improve as well. But that costing was using essentially that toric code. It's called the surface code, this planar version of it. So that was only one logical qubit per block.
And are there like any like principal bounds?
So in the classical world, the analogous thing was Shannon's theorem, which he came up with essentially at the start of the error correction field in the 50s, right? He says these good codes actually do exist, right? No such theorem exists in the quantum realm yet, but there are results which show that codes that are better than the ones that we know definitely do exist. So this one logical qubit and many logical qubits with can be beaten with a good distance as well. So that's definitely known, but it's not linear in n. So what you want is your rate to be linear in n and your distance to be linear in n as well. And that's not known whether or not that exists or
not. I've got a question from Slido. It's anonymous, but could you explain once more what you mean by syndrome?
Yeah, sure. That's just, sorry. That is just, so you make the measurement on the ancilla qubit, right? And the measurement on the ancilla qubit, so I'm measuring in the Z basis here. So my state's either going to collapse in the ket 0, it's going to collapse in the ket 1. If it collapses on the ket 0, basically a bit 0 comes out. If it collapses on the ket 1, a bit 1 comes out. And so the syndrome is just all that bit string after making those measurements. Okay, so if here it was in the state 0, 0, and I made that measurement, the syndrome would be 0, 0. If the state was in 1, 0, and I made the measurement, the syndrome would be 1, 0.
On to the next talk. So let's thank Neil again. Randolph, no talk. Thanks, Neil.
Yeah, no, it's-
You stay?
yeah, for a couple of hours. I have to get back.